Lesson: Deep Learning Techniques in Anomaly Detection. Deep learning techniques are transforming anomaly detection in cybersecurity, providing powerful tools to identify and respond to threats within increasingly complex digital environments. Anomaly detection is critical in cybersecurity as it involves identifying patterns in data that do not conform to expected behavior, which often indicates potential security threats such as fraud, network intrusions, or system failures. Deep learning models, with their ability to learn intricate patterns and representations from vast datasets, offer significant advantages in this domain. Deep learning techniques, including autoencoders, convolutional neural networks, and recurrent neural networks, have shown great promise in detecting anomalies. Autoencoders, a type of neural network architecture, are particularly effective for anomaly detection because they learn to compress data into a lower dimensional form and then reconstruct it. This allows them to learn the typical structure of the data, making deviations from this structure easier to spot. For instance, autoencoders can be trained on normal network traffic data, and anomalies can be detected when the reconstruction error of a new data point exceeds a certain threshold. Furthermore, CNNs, widely used in image processing, are now being adapted for cybersecurity applications. They excel at capturing spatial hierarchies in data, which is beneficial in anomaly detection when dealing with structured data, such as logs or packet captures. By applying CNNs to these data types, cybersecurity professionals can extract meaningful features that may indicate the presence of an anomaly. For example, CNNs can be used to analyze system logs for unusual patterns that suggest a security breach. A practical application of CNNs in anomaly detection can be illustrated with the use of TensorFlow, an open-source machine learning framework. TensorFlow provides pre-built modules and libraries that facilitate the development and deployment of CNNs, allowing professionals to build robust models for real-time anomaly detection. Recurrent neural networks, known for their ability to process sequential data, are particularly suited for detecting anomalies in time series data, such as network traffic or user activity logs. RNNs and their variants, like long short-term memory networks, can capture temporal dependencies, making them adept at recognizing anomalies that evolve over time. In practice, RNNs can be implemented using frameworks like PyTorch, which offers dynamic computation graphs and efficient handling of time series data. PyTorch's flexibility allows cybersecurity analysts to design custom RNN architectures tailored to specific anomaly detection tasks, such as identifying unusual login patterns that could indicate compromised accounts. In addition to these core techniques, generative adversarial networks are emerging as a novel approach for anomaly detection. GANs consist of two neural networks, a generator and a discriminator, that are trained simultaneously. The generator creates synthetic data samples, while the discriminator evaluates their authenticity. This adversarial process enables the model to generate realistic normal data samples, making it easier to identify anomalies as deviations from these generated samples. GANs can be particularly useful in scenarios where labeled anomaly data is scarce, allowing for unsupervised anomaly detection. A practical example of applying GANs in cybersecurity is using them to detect financial fraud by generating typical transaction patterns and identifying outliers. Real-world applications of deep learning in anomaly detection highlight their effectiveness in enhancing cybersecurity measures. For instance, a case study involving a large telecommunications company demonstrated the use of autoencoders to detect network intrusions. By training the model on normal network traffic, the company could effectively identify anomalies indicative of intrusion attempts, significantly reducing the time to detect and respond to such threats. Similarly, the deployment of LSTM networks in a banking environment enabled real-time detection of fraudulent transactions, improving the bank's ability to mitigate financial losses and protect customer accounts. The integration of deep learning techniques into cybersecurity practices requires a comprehensive understanding of both the tools and the data. Frameworks such as Keras, which provides a user-friendly interface for building deep learning models, can facilitate the implementation process. Keras allows professionals to experiment with different neural network architectures, optimize model parameters, and evaluate performance metrics, ensuring that the chosen model effectively meets the specific needs of the organization. Furthermore, practical tools like Apache Spark and its machine learning library, MLlib, offer scalable solutions for processing large datasets, which is often a requirement in cybersecurity operations. By leveraging Spark's distributed computing capabilities, organizations can efficiently train deep learning models on extensive historical data, enabling more accurate anomaly detection and reducing the risk of overlooking potential threats. Despite the advantages, deploying deep learning models for anomaly detection does present challenges. These include the need for substantial computational resources, the potential for high false positive rates, and the difficulty of interpreting model decisions. Addressing these challenges requires a strategic approach, such as incorporating domain knowledge into model design, using ensemble methods to combine different models, and implementing robust validation techniques to ensure model reliability. In summary, deep learning techniques offer transformative potential for anomaly detection in cybersecurity, providing tools that can learn complex patterns and respond to evolving threats. By utilizing frameworks such as TensorFlow, PyTorch, and Keras, and applying models like Autoencoders, CNNs, RNNs, and GANs, cybersecurity professionals can enhance their ability to detect and respond to anomalies effectively. Real-world applications demonstrate the significant impact these techniques can have on reducing detection and response times, ultimately strengthening organizational security. As the landscape of cybersecurity continues to evolve, the integration of deep learning into anomaly detection strategies will become increasingly critical, offering a proactive approach to safeguarding digital environments.